Now that we've investigated for bending and shear with beams, the next step is to calculate deflection. I'm going to walk you through the example 4 from the book. I already have our given filled out. So our first step is to calculate the maximum moment, which is this equation here, which I handed out a list of all these simple beam equations. If you look at figure 1, that's got a uniformly distributed load across the entire beam. To calculate for maximum moment, we're going to take, in our case, so here it was little w, so pounds per linear foot times length squared divided by 8, but we already have big W, so it's going to be big W times L divided by 8. So if I go back here, I got big W times L times 12 to convert it to inches, because we have it in feet, divided by 8. So I'm going to put that in there. Times length times 12. You don't need the parentheses. I put them in there to show you that that's what that's doing, where the 12 comes from, divided by 8. There's the answer for that. If you look in the book, that matches up. Next step, section modulus, like you did for bending, so we can find what beam we want. So that's our maximum moment divided by our allowable bending stress, which we're still using that A36 steel, so it's still 24,000 psi. Alright, so we got 50 cubic inches. So we're gonna, let's just stick with, the book ends up with the W-shaped beam, so let's stick with W-shaped beams. So in our chart over here, we can go click on this. It might look a little different in yours. I'm using the Mac, but you should be able to click on the button like that, and something like this will pop up. I'm gonna go in between 50 and let's just say 60. There, that narrowed it down. I'm going to sort this column A to Z. So we got a 12 by 40. Let's see here. The book uses, so that's 40 pounds per linear foot, 58 pounds per linear foot, 49 pounds per linear foot, or down here at the 14 by 38, 38 pounds per linear foot. I suppose there's also the 16 by... Well, those are taller, so maybe we could say what we're using our beam on, that doesn't fit. So, I mean, all these would work, but we're going to go with this 14 by 38. So now that we know what beam we want, we'll come back here, click on this, select our beam. Now to calculate our max V, if you go to that handout I gave you, you can see that V equals little w times L, which is just big W on ours, divided by 2. Which that also, as you see here, equals your reactions. So reaction equals big W divided by 2. So they both equal that. And V equals one of those. Alright. So to calculate your actual unit shearing stress, to make sure that that beam passes shear, we're going to take max V divided by the beam depth times the width of the beam, the width of the web of the beam. So that's going to be, this divided by, if we go over here to our diagrams, find 14 by 38. Our D column there times the TW there. Click there. Press enter. I forgot to put in my parentheses. It's going to put it in for me. There we go. So that's a little different from the one from the book, but let's see here. I didn't click on the wrong stuff, did I? 14.1. He has 14.12. And then I have 3.1. His is 0.313. So that's the reason it's a little different. But it still passes shear because our allowable shear is, where's that at again? 14,500 psi. Alright, now to calculate deflection. Allowable deflection is the length over 360. So if our length is 20 feet divided by 360, that's 0.06 feet. And then I put these two cells so you can separate those. So to convert it to inches, multiply it by 12. So our allowable deflection is 0.67. Now to calculate our deflection on our beam, it's 5 divided by 384, which is a constant, times W, or total load, which I have in a comment here if you hover over that. L is length, E is modulus elasticity, and I is moment of inertia of a section, which you can find in the chart. So I'm going to type in 5 divided by 384 times big W times length times 12 to convert it to inches. Let's put parentheses around that. Raised to the third divided by our modulus elasticity, which is right here. That's going to be a constant with the A36 steel. And times our moment of inertia, which we'll find in the chart here. So that is, here it is. This is your moment of inertia column, the IXX. IXX 385, close parenthesis. Throw some more parentheses in here. Make sure all that gets calculated correctly. There we go. So that should probably be, let's put parenthesis there, 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 and there. Okay, so as you can see, this number is bigger than that number, so our beam is good. Next, I'm going to show you how to put that into SolidWorks so you can check your math in SolidWorks with this as well. So here I have my beam, the 14 by 38. I made mine using the sketch from the structural steel button from the SolidWorks toolbox. So it gives me my profile, I pop it in there. You also could use, although I find it a little clunky in the way it works, if you go to your design library tab over here, toolbox, ANSI inch, and then down here we have structural members, steel. That should bring up this dialog. You can change how it looks. It might look like that. I prefer a list and small icons. Double click on W section. You can drag it in, ask you that, or you can right click on it. If you drag it in, it doesn't bring in the size you're looking for. So if you click on create part, at least I haven't figured out exactly how to make it work for just dragging it in. It might be possible. So if you right click create part, you can select your shape from here, give it a length and a file name. So if that's something you want to try, it's there for you. So I prefer just using this, plop in the sketch and go from there. Okay, so I already started my static simulation. I applied the A36 steel to my beam. I made it, treated it as a beam, selected my joints, made them both ends immovable, applied my load, and then I'll right click. It's already been run, but I'll run it again. So here's my stress. See, that's good. And then if I show my displacement, it's a little different from what we calculated, because there's probably a lot more going on behind the scenes with SolidWorks. But this number is still underneath our 6.7 allowable deflection. So if you're uncertain about your number, you can throw this all into SolidWorks and see what SolidWorks gives you.